So let me know when to start. Shall I start?
Yeah, you can start. There are about 41 participants now. You can start.
Okay. Good morning to all of you. So I'm Gulab Dewangan. I'm a faculty member at IUCAA. Today I'm going to talk on active galactic nuclei. So, what are active galactic nuclei? In order to understand this, we should, of course, astronomy is mainly observational based. So we should look at observations, and if we, let's say, use a small telescope and take a short exposure of galaxies, and in the case of normal galaxies, what we see is either a diffuse emission, of course, with the central region somewhat brighter, or no emission at all. While in the case of active galaxy, what we see in a short exposure is a point-like or a star-like object. And if we keep on increasing the exposure, in the case of normal galaxies, you see more and more diffuse emission. And if it is a spiral galaxy, you will start seeing spiral structures. While in the case of active galaxy, the point-like source becomes brighter and brighter, and then finally we start seeing the host galaxy, which can be a spiral galaxy. So you will see spiral structures. So that the observationally, the main difference is that in case of active galaxies, we see a very bright nucleus, which kind of overshines the rest of the galaxy. While in a normal galaxy, we see the more of a diffuse emission, and of course, the central region is bright, but not like a star-like nucleus what we see in active galaxies. So this is the main difference. So it kind of indicates that there is a very powerful radiation source at the centers of active galactic nuclei, and these galaxies are called active galaxies, and of course the nuclei are called active galactic nuclei, or in simply AGN. So the phenomena of activity, nuclear activity in galaxies is not just demonstrated by the presence of very bright nucleus. There are other signatures. For example, sometimes we see a jet-like structure emanating from the central region, from the very central region of the galaxy, or from the very nucleus of the galaxy to outer regions, which can extend to even megaparsec scales. So this is another observational characteristics of active galactic nuclei. If you look at the spectrum of this nucleus, the active nucleus, we see in many cases we see very strong emission lines. Many of them can be broad, and some of them can be narrow as well. And we will see how does the optical ultraviolet spectrum looks like. But in case of AGNs, we see strong emission lines, which can be broad as well as narrow. While in case of normal galaxies, mostly we see weak continuum and absorption lines. These are another differences. So what we see about a nuclei of a galaxy, a nucleus of a galaxy is called an AGN. If there is some kind of an activity which is substantial in some observationally determined way. For example, as I mentioned, very bright point-like nucleus, jets from the nuclei, as well as broad emission lines. Sometimes through there may be dust lens passing through the very central regions. So if you look at in the optical ultraviolet, this dust lens may obscure the the active nucleus or very bright nucleus, and you wouldn't see very bright nucleus. In such cases, if you observe the galaxy and the nuclear regions of the galaxy in X-rays, for example, because X-rays can penetrate obscuring material, so you will again see very bright nucleus in the X-rays and some diffuse emission in X-rays, of course. So again, the presence of very bright nucleus in X-rays is also obviously indicates the presence of an active galactic nucleus. So there are a number of classes of active galactic nuclei, but I'll just briefly mention only 2 or 3 types. So one of the very common common AGNs are called Seyfert galaxies. They are mainly hosted by spiral galaxies, and their luminosity that is the luminosity of the nuclear source is comparable to the luminosity of the entire galaxy. For example, our Milky Way has about 10 to the power 11 stars, and each star has, let's say, typically luminosity like our sun's luminosity. So you will, the Milky Way then has a luminosity of 10 to the power 44 arcs per second. And this much luminosity can be emitted by the nuclei in Seyfert galaxies. So therefore, we say the luminosity of the AGN is comparable to the luminosity of the entire galaxy in case of Seyfert galaxies. The other type of AGNs are called radio galaxies. Their name, as their name suggests, they emit powerful radio emission. Then there are the quasars, which can be radio quiet as well as radio loud. The Seyfert galaxies here are actually radio quiet agents. What are the quasars? Quasars actually, the name arises from quasi-stellar radio sources, QSO, or quasars are QSOs. QSOs are called quasi-stellar objects. So they are much brighter compared to Seyfert galaxies or radio galaxies. Their luminosity from the AGN itself can be 100 times the luminosity of the entire galaxy. You see, in case of Seyfert galaxy, the luminosity of the AGN is about comparable to the luminosity of the entire galaxy, while in more powerful agents like quasars, the luminosity is about 100 times the luminosity of the entire galaxy. Now, the Seyfert galaxies were actually discovered with their optical spectrum. And here are the examples of the optical spectrum of a Seyfert galaxy. When we say spectrum, this means it is a plot of the flux density of lambda. F lambda, of course, the flux is a function of wavelength. So this plot of this flux is a function of wavelength. We call this as a spectrum. And you will notice in the upper panel that, first of all, this continuum is very strong. So the spectrum, when we say there is, of course, the spectrum will have two parts. One is the continuum, and then line emission. Lines can be emission lines or absorption lines. In this case, we see very strong continuum and strong emission lines. Strong emission lines, for example, due to the Balmer line, H alpha line, H beta line. These lines, I'm sure you are familiar with. These lines, and again, you see, you look at the profile of these lines, it's obvious these lines are very broad. And in velocity units, the widths, typical widths are about 5,000 kilometers per second. And if you look this with line widths from one AGN to another AGN over an entire population of AGNs, this line width varies from a few thousand kilometers per second to 10,000 kilometers per second or so. So the important point to remember is that in Seyfert galaxies, particularly so-called type 1 Seyfert galaxies, the line widths of the Balmer lines are of the order of 5,000 kilometers per second or so. In addition to these broad emission lines, you see there are narrow emission lines. For example, this line, one of the strong lines is due to oxygen 3 at 5007 angstrom. This line is much narrower, and the width of these narrow emission lines is about 500 kilometers per second. So the Seyfert galaxies, but particularly type 1 Seyfert galaxies, have two sets of emission lines. One set has a broad width about 5,000 kilometers per second, and another set of emission lines which are narrow with a width of about 500 kilometers per second. And here in the bottom panel, slightly expanded view is shown. Again, you see the same lines, of course. But I wanted to show here, to go to the short wavelength region below about 4, there is a rise in the continuum. This particular rise in the continuum looks like a bump, and it is called a small blue bump. So there is something called big blue bump. We will discuss later. But this small blue bump is essentially made up of Balmer continuum and iron 2 emission. The iron 2 and the singly ionized iron has lots of transitions falling in this band, and it is not possible to separate all the huge number of emissions. So they appear as a blend. And another component, which is the Balmer continuum, that means the radiation, the continuum radiation arising from due to transitions from electrons at infinity to n equal to 2 level. So that the radiation resulting from these transitions and the numerous transitions from iron to iron, it constitutes this small, so-called small blue bump. Then let me discuss a little bit about the radio emission in galaxies. The radio emission was discovered in 1933 by Carl Jansky from our galaxy. So this radio emission was essentially of the power law form. When we see that, so that means that when we look at the spectrum of this radio emission, then spectral shape in the radio region is a power law form. That means the flux density to the power some index like alpha or so. So that is the characteristic spectrum. And then when people looked at the polarization, they observed high polarization. These two characteristics are sort signature for synchrotron synchrotron emission. That means the electrons gyrating in relativistic electrons gyrating in magnetic fields. So this is the characteristic synchrotron radio emission with a power law form. And this radiation is, of course, arises due to relativistic electrons and moving in the magnetic fields. And that's how, because these radiation was responsible, the radiation actually arises due to high energy relativistic particles, and the detection of radio emission from galaxies kind of gave birth to so-called high energy physics, because we could now study high energy electrons by observing radio emission. When there were radio surveys, subsequent radio surveys, people found large number of sources, different kinds of sources. Some of these radio sources were associated with supernova remnant, for example, Cassiopeia A. And that's naturally you explain, you expect this synchronous radio emission from supernova remnants, because in the remnants there are high energy electrons which are moving in magnetic field, will give rise to this kind of supernova, this kind of synchronous radiation. But some of the radio emission or the radio sources were associated with galaxies. For example, the Cygnus A, the radio source, one radio source was associated with this galaxy called Cygnus A at a redshift of 0.057. And when people image this galaxy, this morphology, radio morphology, was very peculiar. First of all, at the center, this center was coinciding with the optical center of the galaxy. And then from this center, there were jets emanating in two opposite directions. You will see the narrow jets here, and then finally the narrow jets will travel to hundreds of kiloparsec, or even sometimes megaparsec. So here you imagine the galaxy. Here, of course, it looks like a pint-like, but if you look at the optical galaxy, image in the optical region, that the size of the galaxy is about 10 kiloparsec. And these jets emanate from the nucleus, that is from the AGN, and then they travel to hundreds of kiloparsec and even megaparsec. And they create this kind of structures at both the ends. These are called lobes. So this extended diffuse radio emissions are called these lobes. And at the edge of the lobe, there are these hot spots. So these are the peculiar characteristics of this radio morphology from AGNs. So the radio galaxies, of course, those are the radio galaxies with strong radio emission, and they are associated with galaxies at the central nucleus, and they are very much powerful than the radio emission from our own galaxy. Because in our own galaxy, the radio emission is diffuse emission arising from the different parts of the galaxy due to the synchrotron process. In radio galaxies, in normal galaxies like our own Milky Way galaxy, the radio power is very small. For example, the radio power at 1.4 gigahertz is less than about 10 to the power 23.3 watt per hertz. While in radio loud AGNs, or the very powerful radio galaxies, the radio power is more than about 10 to the power 25 watt per hertz. And there are, of course, also galaxies with the radio power between these two numbers, and they are called weak radio galaxies. So the important thing to remember is that the powerful radio galaxies, which we also call radio loud agents, are much more powerful, like something like 100 times or so compared to the radio emission from normal galaxies like our own galaxy Milky Way. Some of the most powerful radio sources were associated with optical star-like objects. First, the radio surveys were carried out, so people discovered large number of objects, and some of these radio sources were, when people looked at in the with optical telescopes, so these radio sources were appeared with star-like objects, and that is why they are called quasi-stellar radio sources, or quasars. And when people image these some of the radio sources in the optical band, as I mentioned, they look like just like a star-like object. Okay, and this is the optical image of a radio source 3C273. This is the source number 273 in third Cambridge catalog. So these, of course, this when we say star-like, so they are compact sources in the visible. And in fact, in this particular object, there was this jet kind of structure was also observed later, noticed later. It was not really noticed before the discovery of radio emission from this object. And when people studied the optical spectrum of this radio, so 3C273, and they when we say they studied optical spectrum, that means they use a telescope with a slit and a grating, and they disperse the light from this radio, so visible light from this radio source, and that's the dispersed light is shown as the spectrum here. So you see there are this black region, so continuum, and then these lines are there, these bands are there, which are the emission lines. Okay, when people looked at initially after taking the spectrum, people were completely puzzled because they could not identify these emission lines. The location of these emission lines were very different from what people knew at that point of time from the laboratory spectrum. So, for example, here is a comparison of the spectrum, optical spectrum of 3C273, and a comparison spectrum taken in the laboratories, let's say. So in the laboratories, of course, we know where does this H beta line, where the H gamma, H delta lines all occur. But correspond in exactly at the same locations, there was no lines, but the lines were at some completely different locations. But when people actually looked at the line separation and pattern, they could actually match these lines, and they found that the lines like this H beta, H gamma, H delta in 3C273 spectrum were actually red-shifted. The observed wavelengths were longer compared to the rest frame wavelength is seen in the comparison spectrum. So there was a huge shift in the wavelength, and that was that, of course, using that one can derive the redshift, because these objects are all moving away from us, and that gives, and due to the Doppler effect, that results in the wavelength shift. And from that, one can calculate the redshift, which is defined as the shift in wavelength divided by the rest wavelength. And from the observations, one of course measures this shift in the wavelength, and lambda 0, of course, rest wavelength. So one can derive the redshift. Once you know the redshift, then you can calculate the distance using the Hubble's law. So D is equal to C, the speed of light, Z is the redshift, divided by H0, which is the Hubble constant. And when you put for the numbers obtained for this radio source 3C273, it turns out the distance of this source is 470 megaparsec. And this had a huge implication. When you say 470 megaparsec, it from at least from that point of standards, this object was a very, very large distance, and still the object looked very bright. So then one can imagine the intrinsic power of this source must be really, really huge. And that one can, of course, calculate, because we are the flux we observed at Earth Once we know the flux observed at Earth, and once we know the distance, we can calculate the intrinsic luminosity, the total luminosity emitted by this particular source. And in astronomy, we measure this observed flux as well as the intrinsic luminosity in terms of magnitudes, the apparent magnitudes and absolute magnitudes. So I will not go into the details. You may not be familiar with the magnitudes, but remember that we have observed flux and we have the distance. So we can calculate the luminosity of that source. And we can compare that luminosity with the luminosity of our own galaxy Milky Way. And that turns out to be that the quasar 3C273 is nearly 100 times brighter than our own galaxy, like the Milky Way. And that power, that is the 100 times more luminosity, is arising from just point-like source. That's another importance. So this is really remarkable. And then people started worried about what is the origin of such huge luminosity from the nuclei of these objects, or these star-like objects, or even like in the Seyfert galaxies from the nucleus of the galaxy. Okay, before going into investigating what is the origin, let's look at some of the more observational signatures. So this is the optical image taken by SDSS of on a Seyfert galaxy called NGC 40451. So here you see this bright nucleus, and of course this spiral structure. And this bright nucleus is not dissolved in visible light, of course, and this is very compact. And from the unresolved nucleus, one can infer that size must be very compact, much less than about 1 parsec or so. These are some of the other images of the Seyfert galaxies taken with ground-based telescopes. In every every Seyfert galaxy, you see this very bright nucleus, and because they have ground-based telescopes, they are not the point source is not very clear, but you see very bright nuclear region in these cases. These are some of the Hubble Space Telescope images of Seyfert galaxies. You see very bright nucleus from this galaxy, and here this central region is also showing the dust lanes shown in the dark lane here. The another one shows very bright nucleus and also ring-like structure. So you can see different kind of structures. We don't really clearly understand these structures found around this nucleus, but some of these structures are probably carrying some information how the central engine is fed in these active galaxies. And the X-ray image I had already shown. In the X-rays, the AGNs look like point sources again. But in radio, of course, these images can be very much extended. So you will have a core nucleus which coincides with the optical center, and then huge structures, lobes, etc., which can have very different kind of shapes here. You actually see a variety of shapes here. Typical morphology is a radio core and a jet emanating from there, and then this lobe-like structures, which can the shapes of the lobes from one galaxy to another radio galaxy could be very different. So the typical signs of nuclear activity in AGNs is, as I mentioned, the large luminosity. The luminosity can be of the order of 10 to the power 42 to 10 to the power 48 ergs per second. That is about 10 to the power 9 to 10 to the power 15 times the luminosity of our sun. So imagine some 10 to the power 9 or 10 to the power 15 suns sitting in the very compact region. Okay, of course, given the size, you cannot put so many suns in the central region. So therefore, the power must be something different from what the energy source of like our sun. So, and this luminosity is something like 1/100th of the luminosity of a typical galaxy to 10,000 times the luminosity of a typical galaxy. This is the range. This is the range of luminosities we observe from AGNs. While we measure this luminosity, there are some complications. For example, if there is a dust lane passing through the central region, then some of the radiation will be absorbed, and we may not be measuring. We may be actually underestimating the the luminosity. And in some cases, there may be effect of this relativistic beaming, or if the source itself is moving very with the very high speed, with relativistic speed towards us, then the radiation will be enhanced in our direction. So that can also, that in this case, it will overestimate the intrinsic luminosity of the central source, central nucleus. So next, let's look at the broadband continuum emission. When we say broadband continuum, again, we look at the spectral energy distribution, or the amount of flux in different bands, and that is what is plotted here. The flux log of this flux nu f nu is essentially the flux as a function of frequency, log of frequency here. So in case of normal galaxy, this solid line here is the spectrum or the broadband continuum of broadband emission from normal galaxy. Why do we see such a shape? When we say normal galaxy, the luminosity is essentially sum of the luminosity from all the stars. And if you look at stars in a galaxy, the stars can have a surface temperature of about 3,000 to about 30,000 or 40,000 Kelvin. That means the range in temperature is changes by an order of magnitude or so. So therefore, these stars roughly emit like black bodies. So these are like sum of black bodies, and you see this kind of emission. So therefore, this emission does not. This emission essentially is confined within confined in a frequency range, which kind of varies roughly about order of magnitude or so, not more than that. So the emission from normal galaxies is confined into narrow range of the frequencies. No more than about no more than a decade in frequencies. For example, if you look at from here, it's like 14 to 15, at least slightly more than that. Okay. But in case of AGNs, active galactic nuclei, for example, the C41 NGC 3783, first of all, the flux is higher compared to a normal galaxy. For example, in the optical band, these black solid finds are at much higher flux. Then, if you go to shorter wavelengths or higher frequencies, these agents emit very strong radiation in the ultraviolet here, in the ultraviolet, in the soft X-rays, as well as in the hard X-rays. Normal galaxies generally do not emit X-ray emission. There will be some ultraviolet emission because there will be some hot stars. But when we go to X-rays, soft and hard X-rays, they hardly have the strong X-ray emission. But AGNs have very strong ultraviolet, soft X-ray, hard X-ray emission. If you come to the radio region, this particular AGN is radio quiet. Even then, it does emit some radio emission. But in radio loud AGNs, you see again a very strong emission, which I have not shown here. So if you compare the broadband broadband continuum emission or the spectral energy distribution of AGNs, the ACDs of AGNs are spectacularly different compared to the ACDs of normal galaxies. And this is another way we find active galactic nuclei. This is another example of the broadband continuum emission. I'm showing this again because this is for a different type of AGN. Now it is a radio loud AGN. We call some of them are called as blazars, where we think there is a strong jet emanating from the central nucleus, and that jet is pointing towards us. In such a case, the emission from the jet completely dominates the emission from the other components like emission lines and all that. So in such cases, you see this optical ultraviolet here, X-rays here, gamma rays here. So these AGNs are very bright from, let's say, infrared from here to all the way, infrared, optical, UV, X-rays, gamma rays, all the way. Also, they have very strong radio emission here. Of course, radio emission in terms of strength is not as energetic is this UV X-rays, but they also have very strong radio emission, the blazars, of course. In addition, I have already shown you the spectrum of some of these agents, and some of these agents have very strong emission lines in the optical ultraviolet. Here, to look into a little more detail, if you look at this optical spectrum of a normal galaxy, that means it has no active nucleus, then the spectrum looks like this. And you see this noisy kind of spectrum. So this essentially shows us that the continuum is very weak here. And on top of that, you see some of these absorption lines due to the stellar due to the stars. So from a normal galaxy, first of all, the spectrum is red. That means the lesser flux in the blue region, and the continuum is very weak with usually with absorption lines here. While if you look at the AGN spectrum like a C41 galaxy here, and you no longer see this noisy kind of spectrum. And this essentially tells us that the continuum is very strong. And as I had mentioned, the spectrum has the broad emission lines, H alpha, H beta, etc., and narrow emission lines. So such AGNs are called type 1 AGN, or in this case, C41 AGN. There are C42 AGN also. They have only narrow emission lines, no broad emission lines. So they are called type 2 agents. Then there are broadline radio galaxies. So these are radio loud agents, but their optical spectrum seems very similar to type 1 agents. They have broad emission lines as well as narrow emission lines. Then there are narrow line radio galaxies. So then, as their name suggests, they are radio loud agents, but show only narrow emission lines here. Then we have another type of agents called BL lake type. These are also called blazars, where I was mentioning that the emission from the jet in these objects is completely dominates the other components, and therefore we see very powerful continuum, more or less smooth continuum devoid of emission and or absorption lines. Okay, so these are some of the important types of optical spectra from active galactic nuclei. The AGNs, almost all AGNs are very powerful sources of X-rays, while some of them are also very powerful in their gamma ray emission. Apart from these characteristics which I have mentioned, some of these AGNs actually show strong variability over the entire electromagnetic spectrum, and their variability time can range from minutes to days, months, and even and years. And here are some of the examples of their variability. And these are the light curves. So when we say light curve is essentially a plot of intensity or flux as a function of time. So we are essentially looking at how is the flux varying as a function of time. This in here, what is shown is X-ray intensity in a way. So X-ray flux, you can say. That is plotted as a function of time in units of days. And here you see there is a huge change in the X-ray flux. So in let's say this is in days. So about in 4 days or so, this object has changed about a factor of 100 or so. Even in very short period, it can change by a factor of more than 100, about 300 or so. So this is a huge variability in short time scales, like few days it can vary by huge factors. This is in the X-ray. So X-ray emission from AGN is highly variable. And when we come to the optical, let's look at here in the bottom right panel. So this is the plot of intensity, 8 different wavelengths. This is the continuum flux at 1360 angstrom, 1840 angstrom, and 2670 angstrom. Again, this continuum UV flux, these are the ultraviolet flux wavelengths. So the ultraviolet flux is changing quite a bit. So the shortest, the continuum flux at the shortest wavelength is actually changing more than the longer wavelength flux here. Okay, this is the optical, the ultraviolet continuum is also changing here. Now, if you look at the line emission, whether the line flux, we looked at H alpha, H beta lines. So there are also lines in ultraviolet, for example, carbon 4 line, Lyman alpha line, magnesium 2 lines. And you look at the line flux are also changing quite a bit. the carbon 4 limonal alpha, these lines, you look at line in this, the emission is actually changing very strongly here. This is the radio light curve of this object BLSA. And again, here you see this is the radio intensity, 3.8 centimeter. And look at the variability, the huge variability in this object in radio. So we see the AGN, so strong variability in X-rays, ultraviolet, radio, and we know this, they vary in optical and at other wavelengths as well. Apart from the variability, there are some of the AGNs. So radio emission, as I mentioned, in case of Cygnus A. So roughly there are about 10 to 15% of AGNs which show very strong radio emission, and with some of them have this kind of a peculiar morphology. And this is the morphology of Cygnus A, which I had mentioned. This point, the central point-like object is called core, and the size of this core is about milli-arcsecond or so. The jets emanating from the center, the narrow jets emanating from the center, can go from parsec scale to kiloparsec scale. And then we have these lobes, this huge lobes. So the lobe to lobe distance can be hundreds of kiloparsec or even several megaparsec from in some of the radio galaxies. So these are kind of the very large structure arising from a single galaxy. I mean, a galaxy like our Milky Way, the size in the optical is about 30 kiloparsec or so. But these jets arising from the nucleus and connecting to these lobes can have size of several megaparsec, huge, really huge structures. And at the edge of these lobes, there can be these hot spots, and the hot size of these hot spots can be kiloparsec scale. When we look at the radio galaxies, there are three distinct regions in these objects. Of course, there's one of this is diffuse lobes on kiloparsec to megaparsec scale, and the narrow jets and arising from this the nucleus and connecting to hot spots. And then, of course, in there's just compact sources coinciding with the optical nuclei. And when people looked at observed these compact sources, what they found is these compact sources are highly variable, and sometimes the blobs would be ejected and they will move out, particularly when when we do not see these lobes. Particularly, imagine if our line of sight is kind of passing along this jet. In that case, we will only mostly see the emission dominated from this nucleus or from this jet. And when people observe something like that, they found that some of these blobs are being ejected from the nucleus, and these blobs actually are moving. And they could actually observe these blobs and this separation from the nucleus to this blob. For example, this is the observation of 3C273 and July 1977, when people again looked at in March 1978. So this blob has moved further away. In November 1978, this blob further moved away, and the distance kept on increasing. So because this separation is increasing with time, one can actually calculate the speed of the speed at which the blobs are actually moving. And there's a great surprise in 1970s and 1980s that these blobs appear to move actually more at its speeds more than the speed of light. In fact, in this case, 3C273, the source component, like this blob, was found to move at a speed of 8 times the speed of light. So there was this hot spot moved in the hot spot in the radio. It moved about 25 light years in 3-year period, and that gave rise to the speed of roughly about 8 times the speed of light. So how does this arise? This apparently looks like violating special theory of relativity, but it is not really violating anything. So to understand this, let's look at this particular geometry. So let's say here we have this radio source, and let's say at t equal to 0, there is this one of the blob is ejected, and that particular event was observed by an observer and if the distance is d from this observer to the source, then that observer will see this event that a blob has been ejected after a time d by c, distance divided by the speed of light. Okay, let's say this is d by c, and let's say that this blob moves with a speed v. So in time, let's say t1, this moves at v times t1, and let's say and then the blob reaches somewhere here, and that particular event, let's say the observer sees at time t2. So this time t2, so that time t2 will be the time this blob took to move from here to here, that time t1, plus the distance of this blob. Now because this blob has moved out from here to here, and our distance to this core, the actual radio source is d, so the d minus the projection of this one, vt1 cos theta, vt1 cos theta divided by c. So that will be the time when this observer will see that this blob has reached separation from here to here, which is given by vt1 sine theta, given that the angle is theta between between the blob's motion and the line of sight. So we are seeing that this component, the separation is actually moving with time. So therefore, we can calculate the transfer speed of this component, and the separation between these two is vt1 sine theta, vt1 sine theta, and the time it has taken to achieve this separation or to reach this separation is time t2, when the observer saw the source has reached here t2, and when it was ejected here at which was observed at d by c. So the difference of these two times, this transverse separation, and this time t2 minus d by c will give us the transverse speed here. So we can write in, because we have this t2 t1 plus d minus vt1 cos theta divided by c. When we substitute this, we get the transfer speed is equal to v times sine theta. V is the speed at which this blob is moving, and divided by 1 minus v cos theta by c. We can maximize this v perpendicular with respect to this angle theta, and we get the maximum value for cos theta equal to v by c. Therefore, this transfer speed, we write this gamma times v. This gamma is essentially the Lorentz factor, and Lorentz factor can be very large if the speed is close to the speed of light. So this transfer speed can be, because gamma can be much larger than 1. So the apparent speed, the apparent transfer speed can be larger than the speed of light, according to this formulation. So this is called the superluminal motion, which is observed in some of these radio loud agents. Okay, so just to summarize the properties of this agent, so they have very large luminosity, which can range from 10 to the power 9 to 10 to the power 15 times the luminosity of our sun. They are very compact. The nucleus is very compact, much less than about 1 parsec. They show broadband continuum emission from radio, infrared, optical to all the way to gamma rays. They have strong emission lines in the optical ultraviolet. We have already seen H alpha, H beta lines, even carbon 4, magnesium 2, etc. lines are very broad and very strong as well. They almost all agents emit X-ray radiation, and a good and some of the agents also are sources of gamma ray emission. Many agents show strong variability over the entire electromagnetic spectrum, and variability time from in different agents can range from a few minutes to days. Particularly the Blazar type agents are highly variable. They can vary in minutes time scale, while the CFERS etc. can vary on hours time scale, and others on, let's say, in days and weeks, etc. About 10 to 15% of agents show strong radio emission. We call them as radio loud agents, and they show huge, some of them show huge structures from kiloparsecs to megaparsec scale. So that's about the observational characteristics of AGNs. So let's now look at the end source of this huge amount of radiation from these AGNs. So first of all, if you want to know the total energy output, so that typically one can say that that will be the luminosity. That means the amount of radiation they are emitting every per unit time, multiplied by the lifetime. Of course, we do not know the lifetime, but what we find that roughly 1 out of 100 galaxies is an AGN. So that tells us, because if you take the age of the universe, that tells if every galaxy goes through an AGN phase, then the lifetime of the AGN phase should be about 10 to the power 8 years or so. So, and if you look at, if you take a typical luminosity of 10 to the power 45 arcs per second and multiply the typical lifetime 10 to the power 8 years, then the total energy output would be about 10 to the power 61 arcs. Okay, the same number we can also reach in a completely different way. We can, because the radio emission from the core jets and the lobes is arising due to synchrotron radiation, that due to the relativistic plasma moving in the magnetic field. So by observing the radio emission, we can find the energy distribution of the electrons in these different components. And once we have the energy distribution of these particles, we can integrate that energy distribution and find the total energy content in the relativistic plasma. That again turns out to be about 10 to the power 61 arcs. So we can say that the typically the total energy output of AGN is about 10 to the power 61 arcs. Okay. The next thing, let's look at the what is the size of this emitting region. Of course, we do not resolve, but we can use time variability that gives us some constant on the sizes of this emission region. Assuming that the variability is caused by some kind of state change in the emission region, and that would of course be caused by a physical process. In that case, there are two time scales which are important. Tau process, this is the time scale for the radiation process, which results finally in this variability. And because the state of that emitting region will first change in, let's say, somewhere in that somewhere in the emission region. Maybe, let's say, if you assume like a spherical emitting region, maybe something changed in the center, and then this change then traveled through the entire region. So the tau process is the time scale for the radiation process, and delta t is, let's say, this is the crossing time needed to cross the emission region. So generally, the tau process, the time scale for the radiation process is much smaller compared to the crossing time. Okay, and now imagine that let's say in our spherical region, something changed. Let's say some t equal to 0 or so, then this change spreads with, let's say, with a speed v, and this speed v must be less than speed of light. Okay, so then the size of the emitting region will of course be the speed times the crossing time, delta t, and thus this size will be less than the c, speed of light, times delta t, because the speed of light is the maximum speed one can have. So for our observed time scale t observed, delta t observed, that will be the sum of tau process and delta t, and tau process is, as I mentioned, is much smaller compared to the crossing time. So in any case, we can write this size must be of the order of c times delta t observed. So the c times delta t observed kind of gives an upper limit on the size of the emitting region. So delta t observed is the variability time scale. So one can take, let's say, the optical flux, let's say, varies by a factor of 2 in, let's say, 1 hour. So 1 hour times the speed of light, that gives the typical size of the optical emitting region. And when we look at the variability in different bands, for example, in the optical ultraviolet band, the variability time scale is observed to be about 1 to 10 days. Okay, depends on different agents, of course. So that implies a size scale of 0.001 to 0.01 parsec. We are essentially multiplying the delta t observed with the speed of light. While when we look into X-rays, then this observed variability time scale is about an hour, much shorter than what we have in the optical band. And when we estimate the size of the X-ray emitting region, this is very, very compact, 10 to the power minus 5 parsec or so. So in the optical, 10 to the power minus 3 to 10 to the power minus 2 parsecs, we go down to 10 to the power minus 5 parsec in the X-ray band. So if you compare this size scale with the Schwarzschild radius for black holes with different mass, and of course Schwarzschild radius is given by 2gm by c square, then we will see that for 10 to the power 6 solar mass, the Schwarzschild radius is about 10 to the power minus 7 parsec. For 10 to the power 8 solar mass, 10 to the power minus 5 parsec. 10 to the power 9 solar mass, 10 to the power minus 4 parsec. So we see here that our size scale inferred from observed X-ray variability time scale is very much comparable to the Schwarzschild radius for a 10 to the power 8 solar mass object. So it's kind of indicates that this X-ray variability is actually occurring in the vicinity of a supermassive black hole. Okay. So before this things came up, I mean, there was people thought about various physical processes or the origin of this huge amount of radiated power, and finally they found that accretion onto supermassive black hole is actually the real origin, actually that is what is providing the huge amount of radiation. So let's go through how some of the basic argument was what people use to reach at that particular conclusion. So as I mentioned, the total energy output from a quasar is at least the energy stored in its radio halo, like something like 10 to the power 61 ergs. Let's say this this huge amount of energy is arising due to the conversion of mass to this energy. In that case, you have to burn completely about 10 to the power 7 solar mass of that much material completely into energy. Then only we will get this 10 to the power 61 ergs. Okay. And nuclear reactions, we know, for example, hydrogen burning has efficiency of conversion of material to energy, which is about 0.6% or so. So if we want to convert 10 to the power 6 solar mass object to entirely into energy 61 ergs using, let's say, hydrogen burning, then we the amount of material, because the efficiency is only 0.6%. So, and if you convert 10 to the power 7 solar mass, we will be left behind by something like 10 to the power 9 solar mass. Okay, so you essentially you perform the nuclear burning in something like 10 to the power 9 solar mass, and out of that only 100 or so will be converted into energy. So in order to produce this much amount of energy, we will be left behind something like 10 to the power 9 solar mass object. And from the rapid variability now, we see that the agents are very, very compact, no more than the size of the solar system. That means this huge amount of mass, 10 to the power 9 solar mass object, must be confined into extremely compact region like our solar system. Okay, so in solar system, of course, the sun dominates one solar mass, let's say, and the other objects are much smaller. So, and we are talking in the similar size, we are trying to put something like billion suns. That's really, really huge. But on the other hand, if you look at the gravitational energy of which is given by this 3 by 5 minus 3 by 5 gme square by r. So for 10 to the power 9, so if you want to let's say gather something like 10 to the power 9 solar mass, then the energy release will be 10 to the power 62 ergs according to this formula. So while you are assembling this huge mass 10 to the power 9 solar mass, because of the attractive nature of the gravitational force, that will result in an energy release of 10 to the power 62 ergs. which is 10 times larger than the nuclear fusion energy what we had with this comparison. So evidently, this more viable process is, of course, the gravitational energy release. So this was argued by Donald Lindenbell in 1969, and he made this famous statement. Evidently, although our aim was to produce a model based on nuclear fuel, we have ended up with a model which has produced more than enough energy by gravitational contraction. The nuclear fuel has ended as an irrelevance. So that's how people concluded that the gravitational energy release as a result of accretion of material would provide such a huge amount of energy. And using this kind of things, we can actually estimate the mass of this object through this limit called Eddington limit. So imagine we have, let's say, a massive object which is accreting material, and that is resulting in the radiation. So radiation will try to push the material outside, while the gravitational force will try to pull inward. So by balancing the outward radiative force with the gravitational inward gravitational force, we can actually estimate or put a limit on the mass. And when we balance this outward radiation force and inward gravitational pull, we obtained the Eddington limit. And let's look into this Eddington limit. Okay, so let's say we have, I think my time is getting up, but let me discuss for a few more minutes. Let's say we have this big mass m, and which is accreting this small mass m, and the inward gravitational force is F gravity, and outward radiative force is F radiation. Of course, F gravity is given by Gmm by R square, and because of the gravitational energy release, the photons arising from the gravitational energy release are scattering off this small mass m, and therefore, you will have this radiation pressure force that can be derived as follows. Let's say L is the luminosity arising due to this accretion. Then the number of photons crossing at some radius r, this is the separation r, it will be L divided by 4 pi square, and because this will be the energy flux, we need to divide by h nu, energy of individual photons. So that gives the number of photons crossing at r. This is the photon number flux, photons per meter square per second. And because these photons will scatter this mass which is being accreted, that is the particles in the mass which are being accreted, and the appropriate cross section is the Thomson scattering cross section. So if you multiply this Thomson scattering cross section with the number flux, we get the number of scattering per second. So we get L sigma t Thomson scattering cross section divided by 4 pi square h nu. And then once we have the number of scattering, we can calculate the momentum transferred in the scattering process. So the momentum transferred from photon to particle per scattering, of course, is h nu divided by c. So therefore, the momentum gained by particle per second, that of course will be the force exerted by photons and particles. We can write then the radiation pressure force. So this is the number of scattering per second, and then momentum transferred per unit in per scattering. Then this multiplication of these things, we get the radiation pressure force, which is L sigma t 4 pi divided by 4 pi square c. So, and when we equate this radiation pressure force with the gravitational force, we equate these two forces, then we get the Eddington limit from this equation, L Eddington, which is 4 pi c Gmm by sigma t. So what this means is that if the luminosity exceeds this limit, exceeds the Eddington luminosity, then the radiation pressure force will overcome the gravitational force, and the object will not be stable, and the material will be thrown out. So in order to, we can calculate this Eddington luminosity, because this is in the speed of light, gravitational constant, mass of the central source, the small mass which is being accreted and Thomson scattering cross section. But what should we be using for this small mass m? So electrostatic forces between electron and proton, of course, bind them. So they act as a pair. So we should use m for the sum of the mass of electron and proton. Of course, proton is much more massive than the electron, so we can write this m as the mass of the proton. Then we have all the numbers, and we can calculate this Eddington luminosity, and this Eddington luminosity turns out to be 1.26 10 to the power 38 m by Emission. That means for one solar mass object, the maximum luminosity is about 10 to the power 38 ergs per second. Okay, unit I am missing, but this is the ergs per second here. So the our sun's luminosity is 10 to the power 33, 4 into 10 to the power 33 ergs per second. So it's much smaller compared to the Eddington luminosity. And once we have this Eddington luminosity, because it relates with the mass, we can put a limit on the mass, because the the object luminosity must be less or equal to the Eddington luminosity. So therefore, the mass must be more than or equal to this L divided by 1.3 10 to the power 38 times Emission. For a typical luminosity of 10 to the power 46 ergs per second, the mass then must be more than 10 to the power 8 solar mass. Okay, so that 10 to the power 8 solar mass is the mass required in order to power that AGN. So, but in order to satisfy this Eddington limit argument, so now we can argue for a physical picture of AGN. So we have the very large luminosities, and if you apply the Eddington limit argument, this tells us this large luminosity tells us there must be large mass, something like more than about 10 million or even 100 million solar masses. And from variability time scale, which this is the source size is very small. So this entire mass is confined into a very tiny region. In physics, we don't know other than black holes, and in this case, supermassive black holes, which will have, of course, a huge mass in a compact region, and therefore, and we have already seen that gravitational accretion can result in energy release, gravitational energy release, which can be converted into different forms of energy like radiation. And therefore, we say that AGNs, the active galactic nuclei at the centers of galaxies, are powered by accretion of material onto a supermassive black hole. Some of the typical numbers to remember: the central supermassive black hole, the mass can range from 10 to the power 5 to 10 to the power 10 solar mass from one AGN to another, from different AGNs. They are powered by accretion. So if you have accretion rate m dot, then the luminosity is given by m dot c square multiplied by this efficiency. Efficiency is about 10% for accretion. Okay. Size scale of these sources, you can typically think of Schwarzschild radius, which is 2 gm by c square. Luminosity is of the order of by Eddington luminosity, which is given by this formula. This here it should be 1.26 in fact. Okay. I think I will close here because my time is over. So if you have questions, you can ask the questions. Santosh, are you there? How do I see the Google Sheet? The email you sent me? Yes. Google Sheet I see here. Yes. Yes. Subrata Sarangi has a question. So, yeah, go ahead,
Yeah.
Subrata.
Okay. Good morning. Good morning, Professor Gulab.
Good morning.
Yeah, actually, I had posted 3 questions in the chat. Anyway, I'm just reading them. In the beginning, you were telling the you are expressing the width of the emission lines in terms of kilometers per second.
Yes.
What is it exactly? I mean, how do we relate the width of the emission lines to some kind of a speed? Is it some Doppler effect or something?
Yeah. So okay, that's a good question. So usually what is happening? So these emission lines are arising from clouds. Clouds are clouds of some kind of material, which are moving around this supermassive black hole. Okay. So imagine something like let's say a circular motion. So when they are moving around this object, and depending on our inclination, of course, the line of sight, their velocity along the line of sight is changing. Okay, and due to the Doppler shift, sometimes due to the Doppler shift, this lines gets broadened because the velocity is changing.
Some material is moving away, some material is moving towards.
Absolutely. So that is essentially due to the Doppler effect only.
Okay, I had two more questions. You were talking about ASO, SO or something. I mean, that is something which I did not know. You are giving some unit, is it? ASO, SO or something.
Units, where did I don't know?
SO, somewhere you were mentioning, is it some atomic unit or something? Anyway, we can ignore that. The other one, you said somewhere that the galaxies, every galaxy passes through AGN phase. Did I catch it correct, or maybe I understood it wrongly, perhaps?
No, you caught it correctly. So see now we know that almost every galaxy has a central supermassive black hole. And it is, I mean, of course, observationally, we don't know, but it is highly likely that almost all galaxies go through an AGN phase wherever we find. Because even in normal galaxies, we find supermassive black hole at the center, but because many of them are not accreting, we do not see activity. Even in our own galaxy, we have supermassive black hole 10 to the power 6 solar mass or so, but it is only weakly active. It's not really an AGN. So like that, many galaxies. In fact, you may have heard in some of the lectures on galaxies, there is a relation called M sigma relation. The mass of the black hole and the velocity dispersion of the stars are actually very much correlated. And that also kind of implies this mass of the bulge of the galaxy is also correlated with the mass of the black hole. So bigger the all galaxies which have bulge, that means they have supermassive black hole. And almost all galaxies have bulge, maybe smaller or bigger. Yes.
May I just have one additional?
Yeah. Go ahead.
I mean, I had heard in some other video lecture some recent result that they have observed at the core of our galaxy Milky Way. Right now, there are only maybe some few number of stars which are orbiting the central galaxy, like a Newtonian gravitational.
Yes.
That Kepler, they follow Kepler, Keplerian orbit and so on. So does that imply that the supermassive black hole at Milky Way, center of Milky Way, it has passed through the AGN phase? I mean, and it has cleared the its vicinity of stars, and all the accretion that would take place. It is over, and the accretion is that stage is complete. We can say that, or still again some of these stars which are orbiting may also get into that accretion later on.
It is possible. I mean, of course, there are very interesting observations. In fact, quite long time back, the stars, a number of stars moving around the central supermassive black hole, some of them going close, some of them further away. In fact, by studying the motion, and you correctly mentioned that they are moving in a Keplerian fashion, and by looking at the motion, they actually measure precisely the mass of the black hole in our galaxy. In to compare in other galaxies, in normal galaxies which are not active, sometimes the star may be captured by the supermassive black hole, and then we observe so-called this tidal disruption events, and they in these days these are one of the important topic in research, and people we observe time to time these events. So it is possible in our galaxy also something like that may happen, but of course the probability is small, so we don't see this kind of things in frequently. And also the AGN activity is most likely episodic, meaning that every million years or so there may be AGN activity. May be induced by mergers of galaxies, and quite likely mergers of galaxies. And there are pretty good observational evidences even in the radio emission. If people look at some of these giant radio galaxies, they see different population of electrons, some low energy electrons of population, some are higher. So and even in the radio image, they see the lobe structures, maybe slightly different lobe structure, which when they calculate the age much is pretty old, and then newer set of lobes. So this and it turns out that these agents may become active and then become dormant, and they take about in every million years or so they become active again. So that kind of thing is very much possible, and it is observationally have been established at least in some agents.
Okay. Thank you, Professor.
Thank you. I don't see other question. So okay, there is Subhadip Datta. Subhadip, go ahead.
Yeah, hello, sir.
Yes.
Sir, can we study the physical parameters of quasars by predicting a model of quasar with the assumption of redshift?
With the agents of the physical parameter, what kind of physical parameters you are talking about? See, just by redshift, we are getting the distance using Hubble's law, and once we have the distance, we are calculating the total luminosity. Then the luminosity is just one thing, of course. Then, in order to understand the central engine, which is the supermassive black hole accreting and emitting in various wavelengths, even forming the jets. I mean, I did not, of course, discuss many of the observational characteristics, because near the supermassive black hole, the gravity is so strong, and general relativity is, of course, acting, and the effects of general relativity, lots of plasma physics things are there. Just by redshifts, we cannot estimate. Of course, we need lots of physics there.
Okay, sir. Sir, I have asked a question before related quasars, but that was not relevant that time. I find that was very relevant to this lecture. Can I ask?
Yes, please.
Yeah. Sir, in some very distinct quasars spectrum, we have found elements. Now, elements synthesizes to stars. So, as we know, quasars are early galaxy-making stage. So, how can there will be a star without having a galaxy?
Sorry. Can you repeat your question? It was not very clear. The last part.
Yeah.
The last part.
Yeah, sir. We have found elements in the quasar spectra.
Yes.
And as we know, elements are synthesized to stars.
Yes.
So, as we know, quasars are early galaxy-making stage. So, how can there will be a star without having a galaxy?
See, first of all, when we say quasars have their host galaxy. Now, in early days, they were, of course, identified with a point-like point-like object which looked like stars. But with deeper observations with larger telescopes, we see the host galaxy, and then the host galaxies actually have already formed. We see huge giant elliptical galaxies at the host of quasars. So stars have formed. I mean, to grow something like 10 to power 8 or 10 to power 9 solar mass, you need long time. By that time, the stars have formed, the galaxies have formed. So the nuclear synthesis, everything has occurred. So we see heavier, not just hydrogen and helium, we see heavier elements, carbon, etc., silicon, sulfur, etc., even iron in quasar spectra, because nuclear synthesis has already happened in these objects, and happening as well.
Okay, sir. Thank you.
Yeah. Any other question? I don't see any other question. So I'm giving a talk tomorrow at the same time. So if some of you have questions, you can ask me right in the beginning tomorrow, and then I can start the lecture. So that way, that will be also a good thing to do. Okay, so thank you. I will close my today's talk here, and we'll see tomorrow again. Thank you.
Thank you, Gulab.
Yeah. Bye.